Have you ever stopped mid-thought and wondered, not what you were thinking, but why you were thinking at all? Why isn't it all just dark? Why do you have an inner movie playing, complete with sights, sounds, feelings, and a running commentary from the voice you call me? This isn't just a late-night philosophical question. It is, perhaps, the single greatest mystery known to science. We can map the brain, trace its signals, and watch it light up with activity. But we haven't the faintest idea how that 3-pound lump of grayish meat generates the technicolor. Surround sound, deeply personal experience of being you. Welcome to the edge of understanding, where the clockwork of the brain meets the ghost of the mind. Today, we journey into a radical, mind-bending, and perhaps beautiful idea, that the secret to our inner world isn't found in the predictable machinery of classical physics, but in the weird, spooky, and wonderful world of quantum mechanics. Could it be that the very fabric of our consciousness is woven from the same threads of uncertainty and potential that govern the universe at its most fundamental level? Prepare to have your reality questioned. Let's begin by drawing a line in the sand. On one side, we have what philosophers and neuroscientists call the easy problems of consciousness. Now, easy is a bit of a misnomer. These are fiendishly complex challenges that occupy thousands of brilliant minds. They involve understanding the mechanics of the brain. How does it process sensory information from our eyes and ears? How does it store and retrieve memories? How does it focus attention on one task while ignoring distractions? How does it control our bodies to walk, talk, or catch a ball? These are, in essence, problems of computation and information processing. We can think of the brain as an astonishingly sophisticated biological computer. We can build models, write algorithms that mimic these functions. And, with enough time and research, we can realistically expect to map out the entire intricate wiring diagram. We can see which neurons fire when you recognize your mother's face, or when you feel a pang of hunger. This is the world of cause and effect, of inputs and outputs, of a biological machine doing its job. But then, you step over that line, and you fall into an abyss. This is the chasm known as the hard problem, a term coined by philosopher David Chalmers. The hard problem doesn't ask how the brain processes information. It asks a much stranger question. Why does all that processing feel like anything at all? Why is there a subjective, first-person experience attached to it? Think about the color red. On the easy problem side, we can explain it. Light of a specific wavelength around 650 nanometers strikes the cone cells in your retina. This triggers an electrical signal that travels down your optic nerve, through various processing centers in your brain, and ultimately activates a specific pattern of neurons in your visual cortex. We can describe that entire pathway in excruciating detail, but none of that explains the experience of redness. Why doesn't that neural firing just happen in the dark, without any inner sensation? Why does it generate the rich, vibrant, and utterly ineffable quality of seeing red? There is nothing in the physics of the wavelength or the chemistry of the neuron that logically necessitates the subjective feeling. This is the mystery. It's the difference between a computer processing the data for red and you seeing it. It's the pain of a stubbed toe, the joy of hearing a beautiful piece of music, the bittersweet taste of nostalgia. These are the textures of our inner world, and classical neuroscience, for all its power, has no explanation for why they exist. It can map the brain, but it can't explain the mind that inhabits it. This profound gap between the physical organ and the first-person experience of being aware is the Grand Canyon of science. And it's into this canyon that some brave thinkers have decided to throw a quantum rope. To understand why anyone would connect consciousness to the quantum realm, we first have to appreciate just how bizarre that realm is. For centuries, Our understanding of the universe was built on classical physics, a world of predictable, solid objects. A ball is either here or there. It has a definite position and a definite momentum. Everything follows clear, deterministic laws. If you know the starting conditions, you can predict the outcome with certainty. It's a comforting, intuitive, and common-sense view of reality. And at our human scale, it works perfectly. But, in the early 20th century, scientists began probing the world of the very small, the realm of atoms and the particles within them. And common sense went right out the window. They discovered that the fundamental building blocks of our universe play by a completely different, and frankly ludicrous, set of rules. This is the world of quantum mechanics. One of its cornerstone principles is superposition. Unlike a classical ball that must be in one place, a quantum particle, like an electron, can exist in a combination of multiple states or locations at the same time. It's not that we just don't know where it is. It is literally in a fuzzy cloud of probabilities, a wave of potential, until the moment it is measured or observed. Only then does it choose a single, definite state. Imagine a spinning coin that is somehow both heads and tails simultaneously, and only lands on one side when you look at it. That's superposition. Then there is entanglement, a phenomenon Einstein famously called spooky action at a distance. You can link two particles together in such a way that they become a single quantum system, no matter how far apart they are. If you measure a property of one particle, say, its spin, you instantly know the corresponding property of its entangled partner, even if that partner is on the other side of the galaxy. It's as if they are communicating faster than the speed of light, linked by an invisible thread that defies our classical understanding of space and time. Finally, there's the uncertainty principle. This isn't about the limitations of our measuring equipment. It's a fundamental property of reality. It states that there's a limit to how precisely you can know certain pairs of properties of a particle at the same time. For example, the more precisely you know an electron's position, the less precisely you know its momentum, and vice versa. The universe, at its core, has a built-in fuzziness, an inherent element of unpredictability and chance. These concepts, superposition, entanglement, uncertainty, are not just philosophical musings. They are experimentally verified facts that form the bedrock of modern technology, from lasers to computers to medical imaging. But they also paint a picture of reality that is probabilistic, interconnected, and profoundly weird. And it's this strangeness, this departure from the clockwork determinism of the classical world, that makes it such a tempting parallel to the elusive and seemingly non-physical nature of our own minds. Could the flickering, probabilistic nature of our thoughts, the feeling of unity, and the sense of free will find a home in this quantum weirdness? The idea of linking consciousness and quantum mechanics isn't a New Age fad. It's as old as quantum theory itself. In the early days, the giants of physics were not just grappling with equations. They were grappling with what those equations meant for the nature of reality. At the heart of their struggle was the measurement problem. As we discussed, a quantum system exists in a superposition of possibilities, described by a mathematical entity called the wave function. This wave of potential evolves smoothly and predictably over time. But the moment you try to observe or measure the system, something dramatic happens. The wave function inexplicably collapses, and only one of all the possibilities becomes real. The big question was, and in many ways still is, what constitutes a measurement? What is the magical ingredient that forces reality to choose? Two brilliant minds, John von Neumann, a towering figure in mathematics and physics, and Eugene Wigner, a Nobel laureate, proposed a radical and unsettling answer. They looked at the chain of interactions involved in a measurement. A quantum particle interacts with a detector, which interacts with a computer, which displays a result on a screen, which creates photons that travel to a scientist's eye, which triggers a signal in their brain. Where along that chain does the collapse happen? Von Neumann and Wigner noted that, in principle, every physical object in that chain, the detector, the computer, the screen, even the scientist's brains itself, made of quantum particles. Therefore, they too could be described by a wave function and exist in a superposition. The detector could be in a superposition of having detected the particle and not having detected it. The computer could be in a superposition of showing yes and showing no. So, where does the buck stop? They proposed a startling conclusion. The chain only ends, and the wave function only collapses. When it reaches something that is not just another physical system, it collapses when it makes contact with consciousness. In this view, the observer isn't a passive bystander. The observer's mind is an active and necessary participant in the creation of reality. It is the act of conscious awareness itself that plucks one reality out of the shimmering sea of quantum possibilities. This idea placed humanity in a uniquely central and almost mystical role in the cosmos, suggesting that the universe, in some fundamental way, requires a conscious mind to become definite and real. It was a breathtaking idea, weaving the observer not just into the experiment, but into the very fabric of existence. While the early ideas of von Neumann and Wigner were philosophically profound, they were also maddeningly vague. They didn't propose a specific biological mechanism. How, exactly, would the brain interact with the quantum world? For decades, the idea remained a fringe speculation. That was until the 1990s, when a highly specific, ambitious, and deeply controversial theory emerged from an unlikely partnership. Sir Roger Penrose, a world-renowned mathematical physicist, and Stuart Hameroff, an anesthesiologist. Their model is called Orchestrated Objective Reduction, or ORC-OR. Penrose was coming from the world of physics and mathematics. He was bothered by the measurement problem and didn't like the idea that a conscious observer was required for collapse. He proposed that collapse, which he called objective reduction OR, is a real, physical process built into the universe's geometry. He argued that superpositions can't grow indefinitely. When a system reaches a certain threshold of mass and energy separation, it becomes unstable and collapses under its own gravity, creating a single, definite state. Penrose saw each of these objective reduction events as a fundamental flicker of proto-consciousness, a raw elemental moment of experience embedded in the universe itself. Hameroff, meanwhile, was coming from the world of medicine. As an anesthesiologist, his job was literally to switch consciousness off and on. He was fascinated by how different anesthetic gases, despite their varied chemical structures, could all erase awareness. He began to suspect they weren't just acting on the connections between neurons, but on something within them. His search led him to a structure called the microtubule. Microtubules are the cell's skeleton. They are tiny, cylindrical protein scaffolds inside every cell, including our neurons. They are crucial for cell structure, transport, and division. Hameroff proposed that these microtubules were the perfect candidates for hosting quantum processes in the brain. He argued that their unique, crystalline structure could shield delicate quantum states from the noisy environment of the cell. Together, Penrose and Hameroff created the ORC, or theory. Here's the gist. They propose that electrons within the protein subunits of these microtubules can enter into a state of quantum superposition. These superpositions become entangled with others in microtubules across many neurons, creating a large-scale quantum state that spreads through the brain. This quantum computation continues until it reaches Penrose's objective threshold for collapse. At that moment, the wave function collapses is orchestrated by the microtubules. This collapse creates a moment of conscious experience. In this view, our stream of consciousness is not a continuous flow, but a sequence of discrete moments. A series of these orchestrated collapses happening over and over, about 40 times per second. Each collapse is a moment of choice, selecting one reality from a superposition of possibilities. And the experience of that choice is consciousness. It's an incredibly detailed and audacious theory, attempting to link the grandest questions of cosmology with the tiniest structures inside our own brain cells. It suggests that consciousness isn't just something the brain does, it's a connection to a fundamental level of reality. So, why would we even entertain such a wild and complicated idea? The primary argument against it, as we'll see, is a powerful one. But the proponents of a quantum brain have some intriguing points that keep the theory alive. First, they point to nature itself. For a long time, it was assumed that quantum effects could only happen in highly controlled, isolated lab settings at temperatures near absolute zero. Biology seemed far too warm, wet, and chaotic for such delicate phenomena. But this assumption is crumbling. The emerging field of quantum biology is revealing that nature has been exploiting quantum tricks for billions of years. The most famous example is photosynthesis. Plants are able to transfer energy from captured sunlight to their reaction centers with nearly 100% efficiency. Classical physics can't explain this. It appears that the energy doesn't just travel down one path. It enters a quantum superposition and travels down all possible paths at once, sniffing out the most efficient route. This quantum coherence is happening in a messy, living leaf. If a plant can do it, why is it so impossible that a brain could? Second, there's the subjective experience of thought and free will. Our minds don't feel like deterministic computers. Our thoughts are not always linear and logical. We have flashes of insight, creative leaps, and a persistent, powerful feeling that we are the authors of our own choices. This sense of freedom and unpredictability seems to resonate much more deeply with the probabilistic, uncertain nature of quantum mechanics than with the clockwork certainty of classical physics. If our brains were purely classical computers, every single one of our thoughts and actions would be predetermined by the state of our neurons a moment before. In a quantum brain, however, each collapse of the wave function introduces a genuine element of chance and choice, a potential physical basis for what we experience as free will. It's a poetic, if not yet proven, alignment between the physics of the small and the feeling of being alive. Now we must turn to the primary, and very powerful argument against a quantum brain decoherence. Quantum states, like superposition and entanglement, are incredibly fragile. They are easily destroyed by interactions with their environment. Stray vibration, a change in temperature, a single wandering particle. This process of the quantum state leaking out into the environment and losing its special properties is called decoherence. It happens astonishingly fast. The brain, critics argue, is the absolute worst place imaginable to try and sustain a quantum state. It's warm, which means lots of thermal vibrations. It's wet, full of charged ions and molecules sloshing around. And it's electrically noisy, with billions of neurons constantly firing. It's a chaotic biochemical storm. Skeptics calculate that any quantum superposition in a structure, like a microtubule, would decohere in a femtosecond, a millionth of a billionth of a second. That's vastly shorter than the timescales of neural processing, which happen in milliseconds. If consciousness requires quantum coherence, it would be like trying to build a sandcastle in the middle of a hurricane. The castle would be gone before you could even perceive it was there. For these skeptics, the answer to the hard problem doesn't require any exotic new physics. They argue that classical neuroscience is more than sufficient. In this view, consciousness is an emergent property. Emergence is the idea that complex systems can exhibit properties that their individual components do not have. For example, a single water molecule H2O isn't wet. It doesn't have the property of wetness. But when you get trillions of them together, the property of wetness emerges from their interactions. A single neuron isn't conscious. It's a simple biological switch. But, the argument goes, when you connect 86 billion neurons, with trillions of synaptic connections, in the staggeringly complex network of the human brain, consciousness simply emerges from that overwhelming complexity. From this perspective, our inner world is the ultimate expression of computational complexity. Our feelings, thoughts, and sense of self are the high-level output of a classical, biological machine. Researchers using tools like fMRI and EEG have made incredible strides in linking specific mental states to observable, classical patterns of brain activity. They can see your brain light up in different ways when you feel happy, sad, or afraid. For many neuroscientists, this is proof that we are on the right track. The puzzle is immense, but the solution, they believe, lies in continuing to map the intricate classical dance of our neurons, not in looking for ghosts in the quantum machine. The debate isn't entirely black and white. While the brain is a harsh environment, the discoveries in quantum biology have shown that nature is cleverer than we thought. As mentioned, plants use quantum coherence in photosynthesis. There is mounting evidence that migratory birds navigate using a quantum compass in their eyes, where entangled electrons are sensitive to the Earth's magnetic field. Our sense of smell might even depend on quantum tunneling, where an electron teleports through an energy barrier to help identify a molecule's scent. These examples prove that biological systems can and do protect and exploit fragile quantum states. This doesn't prove the OR theory is right, but it does weaken the decoherence argument. It leaves the door for a quantum brain cracked open, even if just a little. At the same time, our understanding of the measurement problem in physics has evolved. The early idea of a conscious observer causing collapse has largely fallen out of favor among physicists. The modern, mainstream explanation is, ironically, decoherence. The idea is that you don't need a conscious mind. Interaction with any part of the environmenta, single air molecule, a stray photons, enough to act as a measurement, and destroy superposition. In this view, collapse isn't a mysterious event. It's a constant ongoing process, as quantum systems interact with the classical world around them. Other interpretations have also emerged that do away with the collapse postulate entirely. The many-worlds interpretation, for example, suggests the wave function never collapses at all. Instead, every single time a quantum measurement is made, the entire universe splits into multiple branches. In one branch, the electron was spin up. In another, it was spin down. Every possible outcome occurs, each in its own separate, parallel universe. In this view, our consciousness simply follows one of these branching pathways, giving us the illusion of a single reality. It's a mind-boggling idea, but one that is taken seriously by many physicists. These modern interpretations remove the special, central role for consciousness that the early pioneers had proposed, making the link between mind and quantum mechanics less direct. This brings us to the most crucial point in any scientific debate. Where is the proof? For all its philosophical beauty and theoretical elegance, the quantum consciousness hypothesis suffers from one major drawback: a lack of conclusive experimental evidence. Science demands testable predictions and falsifiable claims. For decades, the search has been on for a smoking gun, a piece of data that could only be explained by quantum processes in the brain. The search has yielded some tantalizing but ultimately controversial hints. Researchers have looked for evidence of quantum effects in microtubules. Some studies have suggested that anesthetics might work by dampening quantum vibrations within these structures, which would support Hameroff's ideas. Other experiments have tried to detect long-lasting quantum coherence in brain tissue. However, these findings are often difficult to replicate and are subject to alternative, classical explanations. The signal is weak, the noise is high, and the scientific community remains largely unconvinced. Without solid, repeatable proof, the quantum brain remains a captivating and brilliant speculation. But it has not yet crossed the threshold into mainstream, accepted science. It's a beautiful hypothesis still waiting for its moment of truth. In recent years, a powerful new challenge to the necessity of a quantum brain has emerged. Not from a physics lab, but from Silicon Valley. The astonishing rise of artificial intelligence, built entirely on classical computation, forces us to reconsider the connection between intelligence and consciousness. We now have AI systems that can compose music that moves us to tears, create breathtaking works of art, write poetry, and master games like Go and chess at a level far beyond any human grandmaster. These are tasks that we once considered the pinnacle of high-level intelligence, creativity, and intuition. Yet, the large language models and neural networks that power them are running on classical computer chips on 1 south and 0 south. On deterministic algorithms, there isn't a single quantum qubit involved. This poses a difficult question. If high-level, sophisticated intelligence can be achieved classically, why should we assume that consciousness, which seems to be a feature of that intelligence, requires an exotic quantum explanation? If a machine can demonstrate creative problem-solving without a quantum brain, it significantly weakens the argument that a biological brain must rely on quantum effects for the very same reason. While no one is claiming today's AI is conscious, their rapidly advancing capabilities suggest that the kind of complex information processing we associate with a mind might be achievable without ever leaving the world of classical physics. The existence of powerful AI serves as a potent reminder of the staggering, and perhaps sufficient, power of pure complexity. Beyond all the physics, biology, and computer science, there is another, more human reason why the idea of a quantum mind is so powerful and persistent. Its deep, mystical, and philosophical appeal. In a world often described by science as a cold, random, and meaningless machine, the quantum consciousness hypothesis offers a profound sense of connection and purpose. It suggests that our inner lives are not just an accidental byproduct of neural chemistry. Instead, it hints that we are connected to the fundamental fabric of the cosmos. It bridges the ancient gap between science and spirituality, between the objective world out there and the subjective world in here. Words from the quantum lexicon, entanglement, superposition, unity are borrowed as rich metaphors for human connection, untapped potential, and a holistic worldview. The idea satisfies a deep human longing to feel that we are not isolated observers of the universe, but active and integral participants in its unfolding story. It makes us feel that the mystery within us is a reflection of the mystery of the cosmos itself. This powerful narrative, this blend of cutting-edge science and ancient wonder, gives the theory a cultural life that persists, regardless of the status of the experimental evidence. So, where does this leave us? On the one hand, a compelling, beautiful, and deeply resonant idea that our minds are quantum systems. On the other, a mountain of skepticism, a lack of hard evidence, and the powerful counter-arguments of classical neuroscience and AI. Perhaps the most reasonable position, for now, lies in a speculative middle ground. It's possible that the truth isn't an either-or proposition. Perhaps consciousness is, as the classical neuroscientists argue, primarily an emergent property of incredibly complex neural networks. But maybe, just maybe, subtle quantum effects still play a crucial, supporting role. In this view, quantum mechanics wouldn't be the source of awareness itself, but it could be a vital ingredient in the recipe. Quantum effects might inject a layer of genuine unpredictability into our decision-making, giving us a physical basis for free will. They might enhance the efficiency of information flow in the brain, much like in photosynthesis. They could be the secret sauce that makes our classical computer of a brain so much more creative, intuitive, and adaptable than any AI we have yet built. This balanced speculation allows for possibility without overstating the evidence. It respects the power of the classical brain while leaving the door open for the universe's hidden tricks. The future of this debate is exhilarating because it lies at the intersection of our two greatest scientific frontiers: the exploration of inner space, the brain, and outer space, the cosmos, as described by quantum physics. As our technologies improve, the questions will become sharper. More precise brain mapping technologies will give us an unprecedented view of the neural correlates of consciousness. At the same time, improved quantum experiments may one day allow us to probe for and even manipulate quantum effects within living biological systems. The conversation will evolve from philosophical debate to experimental science. A final answer may still be distant, but the path toward it promises to be one of the most exciting journeys in human history. In the end, regardless of whether our consciousness is born from the classical dance of neurons or the spooky waltz of quantum particles, the simple fact of its existence is the most profound wonder of all. The universe is made of stardust, and for a brief moment, that stardust can wake up. It can look back at the stars and wonder where it came from. It can feel love, create art, and question its own place in the grand scheme of things. Perhaps the ultimate lesson from this journey is not about finding a definitive answer, but about learning to live with the beauty of the mystery. The quest to understand consciousness teaches us humility. It reminds us that there are vast territories of reality that remain beyond our comprehension. It also inspires curiosity, urging us to keep asking the big questions, to push the boundaries of our knowledge, and to never lose our sense of wonder at the simple, staggering fact of being aware. Knowledge and wonder are not opposing forces. They are inseparable companions on the human journey. The search for the source of our inner world is a mirror. It reflects our deepest desires for meaning and connection. It challenges us to think critically, to weigh evidence, and to remain open to radical new ideas. And it invites us to appreciate the here and now, this fleeting moment of subjective experience. Whether it's a quantum collapse or a neural cascade, the feeling of the sun on your skin is real. The sound of a loved one's laugh is real. The richness of this inner life is the greatest gift we have. So, as you go about your day, I invite you to pay a little more attention to that inner world. What does it really feel like to be you, right now? And what do you think is at the heart of it all? Is our consciousness a ghost in the machine, a fluke of complexity, or a bridge to the fundamental reality of the universe? Thank you for joining me on this journey to the very edge of what we know. I wish you all the very best of health, happiness, and continued curiosity. If you enjoyed this exploration and want to dive into more of life's greatest mysteries, please consider subscribing to the channel. Until next time.